All right, today we're diving into a small but super important device that you'll find at the heart of modern automation, the tachogenerator. It's really the secret sauce behind how machines can control their speed so precisely. So let's get into it. I mean, seriously, think about that for a second. How does a complex machine, whether it's a giant factory robot or even the elevator you ride in, control its speed with such perfect accuracy? It has to have a way to measure, constantly, how fast its parts are spinning. Well, this little guy is the answer. This is a tachogenerator. At its core, it's a small electromechanical generator. It's got one job and one job only: measure the rotational speed of a shaft and turn that physical motion into an electrical signal. You can think of it as a speedometer, but for machines. So how does this clever little device actually pull this off? Well, to really get it, we've got to pop the hood and take a look inside. And here we go. Once you take the casing off, you can see all the core components. It kind of looks like a tiny electric motor, doesn't it? But here's the twist. Instead of using electricity to create motion, it does the exact opposite. It uses motion to create electricity. Okay, let's break down how these parts work together. You've got the shaft, which hooks up to whatever machine we're trying to measure. That shaft spins the rotor. You'll also hear it called an armature, and it spins inside a magnetic field that's created by the stator, which stays put. Now, in the DC models, you've got a commutator and brushes, and their job is to collect the electrical signal that gets generated and send it on its way. And that brings us to the really cool part, the fundamental physics of it all. How does just spinning something inside a magnetic field actually give us a useful, precise measurement of its speed? This diagram of a DC tachogenerator lays it all out. See, the shaft that's connected to the motor we're measuring is spinning the armature. The copper wires on that armature are literally slicing through the magnetic field from the permanent magnets. And that simple act, a wire moving through a magnetic field, is what induces a voltage. This is the key scientific principle making it all happen. It's called electromagnetic induction, and it's the very same idea that lets massive generators at a power plant create electricity for entire cities, just, scaled way, way down to something you can hold in your hand. Now, that formula on the left might look a little intense, but here's the beautiful part. That formula includes a bunch of stuff about the device itself, like how strong the magnet is, how many wires are in the coil. But once the tachogenerator is built, none of that stuff ever changes. It all just gets bundled together into one single constant. And what that means is all that complicated math just melts away. It boils down to this one beautifully simple relationship. The voltage it generates is directly proportional to the speed it's spinning. That's it. You double the speed, you get double the voltage. You cut the speed in half, you get half the voltage. Simple as that. And here's what that perfect relationship looks like on a graph. The output voltage versus the speed is a practically perfect straight line. This linearity is the secret to why the tachogenerator is so incredibly accurate and reliable. You can always trust that a certain voltage means one and only one specific speed. Now, these devices aren't all exactly the same. They generally come in two main flavors, DC and AC. They both get the same job done, but they just go about it in slightly different ways. So, let's put them head to head. The DC version, which is what we've mostly been looking at, uses those brushes and the commutator. Its biggest perk is that the polarity of the voltage, whether it's positive or negative, tells you which direction it's spinning. Super useful. The downside? Well, brushes are physical parts that wear out, so they need maintenance. The AC version, on the other hand, has no brushes at all, which makes it way more durable and lower maintenance. The trade-off is you lose that built-in direction info. So in the AC design, it's actually the magnet that rotates while the coil, the armature, stays stationary. This setup creates an alternating current without any parts physically touching and rubbing together, which is why it's so robust. That AC signal is then usually converted to DC by an external circuit for the control system to use. Okay, so we've got the how down, but where does this tech actually matter? Where does it make a real-world impact? The answer is pretty much anywhere that things need to move with precision. I mean, they're the unsung heroes inside motor control systems, making sure a conveyor belt moves at a perfectly steady pace. They're critical in industrial robots, allowing them to make those exact, repeatable movements over and over. They're in CNC machines carving out intricate parts, and yep, they're in the elevators we ride in every single day, making sure that ride is smooth and safe. When you get right down to it, it's all about this. Tachogenerators provide the essential feedback for any control system. The system tells a motor, hey, turn at this speed. The tachogenerator reports back and says, here's the actual speed. And the system is constantly making tiny corrections based on that info. It's this nonstop conversation that makes all of modern automation possible. The tachogenerator really is a perfect example of what we call a transducer, a device that just converts one form of energy into another. In this case, it's turning kinetic energy into electrical energy, all for the purpose of measurement. It really makes you wonder, right? What other simple, elegant devices like this are out there, quietly translating the physical world into the data that powers our lives?